In this video, we're going to learn how to write our own hardware interface for ROS2 control. Now, if you don't know what a hardware interface is, or why you'd want one, or even what ROS2 control is, then I recommend you pause this and check out my other tutorial on ROS2 control first before coming back. In that tutorial, I just provided a hardware interface, and since then I've shown you where you can find updates and that sort of thing. But what if your hardware is different to mine? Or what if an update comes along and breaks things? You want to be able to get in there and change things around, or even write one yourself. So today I'm going to walk through step by step how you go about creating your own hardware interface. Now, be aware that this will involve writing C++ code. Unlike the rest of ROS, you can't use Python here, at least not that I know of. And as much as I'll try to explain things clearly, having some C++ experience will serve you well. Something else to be aware of is that ROS2 control is still very much under active development. So while the concepts in this video will probably stay the same for a while, some of the actual code and details might change in the future. Lastly, this video is sponsored by PCBWay, more about them later. Before we actually look at any code, let's recap what a hardware interface does. ROS2 control gives us a system that abstracts controller design from hardware interactions. A hardware interface or hardware component is a plugin written in C++ for a specific model of hardware that exposes that hardware's functionality in a standard way. So we're talking about things like position or velocity, and they can either be exposed as a feedback value that comes from the hardware, these are called state interfaces, we read them, or a command value sent to the hardware, these are called command interfaces, and we write to them. When a hardware interface plugin is loaded up, we can see what interfaces are exposed and whether any of the ROS2 control controllers are currently connected to them. One other thing to know about hardware components is that they have a state very similar to ROS2 lifecycle nodes, if you're familiar with that. And whenever we transition from one state to another, a function gets executed. We get to choose what that functionality is. We're going to write that code. So here's a simplified version of the states and the functions that get executed as we go between them. OnInit runs when we move from the startup to the unconfigured state. This is where we read in input parameters, allocate memory, that sort of thing. OnConfigure takes us to the inactive state. This is usually where we open up comms to our hardware. OnActivate takes us to the active state. This is where we engage any actuators. While we're in the active state, this is where we're reading and writing and controlling our hardware. Then OnDeactivate takes us back to the inactive state, disengaging any actuators. OnCleanup takes us back to the unconfigured state, disconnecting comms. And OnShutdown shuts down the whole thing. If you don't implement a particular function, that's okay, it'll just do nothing. And just a disclaimer, this is my interpretation of the ROS2 control documentation. As I said, this is all evolving and the standards may change, but that's the process I'll be assuming for this tutorial. So today we're going to look at how to write a custom hardware interface for whatever kind of hardware you've got. In my case, I'll be rewriting an existing one that I created for an earlier version of ROS. Nominally, it's designed for a differential drive robot, although I guess you wouldn't have to use it with that. It's just designed to use serial comms to talk to two motors, each of which have velocity control and position and velocity feedback. We're going to kind of cheat by copying one of the ROS2 control examples. These are a great way to get started with ROS2 control, and especially with writing a hardware interface. So I'm here on my dev machine at the github.com/roscontrols/ROS2control demos. And if we scroll down to the README here, we can see example 2 is a diffbot. Diffbot or differential mobile robot is a simple mobile base with differential drive. It's pretty much exactly what we want. So what we want to do is get a copy of this onto our computer to work on. Each of these example directories are their own package that you can get separately. So there's a few ways you can do that, but I'm going to do it just by cloning it in the terminal. I've made its own workspace here, so then I'm going to move the example directory, so that was example 2, into my current directory. So you can see how now I've moved example 2 out, and then I'm just going to delete the original. So now we should just have example 2 there. We can hop back into the root of the workspace and build it with Colcon. Then we can source our workspace and launch it with ROS2 launch ROS2 control demo example 2 diffbot.launch.py. It's editing Josh here. I didn't really explain what it is that we're launching. The main functionality of this package is the hardware component plugin. Now, testing a plugin like this can be tricky, so it also comes with an example URDF, parameters file, and launch file so that you can run it easily on its own. Then, when you're building a robot and you include this package, you can just link to the plugin and ignore the other bits. This particular hardware component simulates a perfect motor. It takes the command velocities and returns the same values as the state velocities, and then integrates those to generate state positions. In our case, we'll be replacing the simulated motors in the plugin with actual motors, but we'll leave all the other example test stuff pretty much the same. Now this is running like a simulated one. It's not using like a gazebo simulator. It's just faking the motions of the wheels. So we can open a new tab and we can run teleop twist keyboard. And we want to make sure we remap the topic. So in this case, that's command vel to diffbot base controller, command vel unstamped. And hopefully when we drive it, we can see our little robots moving around. So ROS2 control is taking in the command velocity, sending it to kind of a virtual motor, which is moving the robot. Now that we've seen it in action, let's open up that directory in VS Code. Before we get stuck into the really meaty code of the hardware interface, let's take a look at what other files are in this that are helping us to run the example. So in the bring up directory, we've got a config directory which has our controller configuration. You'll recognize this from the ROS2 control tutorial, very similar. So we've got a joint state broadcaster and the diffbot base controller, which is a differential drive controller. Then we've got a launch script, diffbot.launch.py. That's what we were running a minute ago. It's going to open up our robot description. It's going to start a controller manager. It's going to start the controllers. In this case, it runs RViz as well. So nothing too crazy there. In our description directory, so we've got a few different things in here. We've got our URDF of our robot. We've got an RViz parameters. But the most important thing here is our diffbot.ros2control.exacro. So this is the little exacro segment that's going to get imported into the rest of our URDF that controls the ROS2 control specific stuff. Again, very similar to what you would have seen in the ROS2 control tutorial. We've got the hardware directory. This is where the actual C++ code lives. And then we've got various other files that are all part of how it is going to compile the C++ code, register it as a package and a plugin, that sort of thing. Let's dig a bit deeper into that C++ code. Often when you want to understand a piece of C++ code, the first place to look is the public interface, and that's the headers. So we're going to go into the include directory, and we see two files in here. There's this one called visibilitycontrol.h. This is something you'll see from time to time on different packages, and it's not something I've really spent the time to properly understand. I know I should, but I believe it's declaring a bunch of macros that restrict the visibility of certain functions in the compiled library. This is done for various reasons, for compatibility and making it run faster and that sort of thing. This just handles that in a cross-platform way. We don't need to worry too much about the details, just be aware that you're going to see these everywhere. The stuff we're really interested in is in diffbotsystem.hpp. So we've got the license at the top, and then we've got our includes. So what are we including? We've got hardware interface stuff. This is the ROS2 control bits we need to make our hardware interface. We've got RCL CPP stuff. So that's just general ROS CPP things. We actually don't need a bunch of these in this case, but they're there anyway. And then we've got the visibility control. So that's just including that header from before that gives us those macros. So this is our class that we're creating. It's diffbot system hardware. That's what the class is called. And it inherits from hardware interface system interface. So there's a few different ones we can inherit from. A system interface lets us read and write to our hardware. And basically what this gives us, it gives us a shell of a plugin that we need to fill in individual functions for. So that's what we're going to see down here. These are individual functions that are overriding functions that live inside this system interface. So we override it and we provide whatever functionality we need. So we've got on init, that's the first of those state transition functions I mentioned at the start. We've got export state interfaces and export command interfaces. So what these functions are going to do, it's going to spit out the list of interfaces that are available so that the rest of ROS2 control knows what it has to read and write to. We've got on activate and on deactivate. that's some more of those same state transition functions or life cycle functions. Then finally, we've got read and write. These are the most important ones. These are the actual commands that we are sending to our hardware and from our hardware so that we can control it and read from it and that sort of thing. All these functions have those visibility control macros on top of them. You can kind of just ignore that, let it wash over it. They just need to be there for the visibility control stuff to work. Finally, we've got our variables down here. So these first two are just parameters that are very specific to this simulated hardware. It's a variable that controls how long the simulated hardware takes to start up and shut down. We'll definitely be getting rid of them. These variables contain our state and command interface values. So we'll be talking more about them later. We're actually going to get rid of them and do them a bit differently. Finally, we've got these other variables for storing the robot position. I'm not really sure why they're there. They shouldn't need to be. They end up just getting passed through as being these hard-coded values. Again, they're only part of this simulated robot. We're going to be getting rid of them for our real one. So that's our class. We've got inheriting from the system interface. We've got a bunch of functions that we're going to override, and then we've got whatever variables we need to create. Now let's take a look at the implementation. If you're not big on C++, this might look pretty scary, but this file is only 239 lines long, and I'm confident that by working through it together, we're going to be able to get our heads around it. So again, it starts off pretty similar. We've got the license, then we've got our includes, and we're pretty much just including the diffbot system header that we were just looking at, and then some other pretty standard sort of things. Our first interesting function here is the initialization. So this is the onInit function. And you can see that this function is getting passed in hardware info. So this hardware info is where we're going to able to retrieve all the parameters that are set in the Xacro file. So if we go back to here, all of these parameters here, so in this case it's the start and stop duration and what command interfaces and state interfaces we want, all of that information is going to be stored here in the hardware info, and we can get it out. So this function is going to execute the onInit of the base class first, and if that fails, then we want to return an error, because if we can't even do that, there's no point moving forward. We initialize some values, and then here we start to pull out this hardware info. So we get the parameters, so it's getting that example param hardware blah blah blah. That was what we saw here. And it's storing that in that hardware start sec variable, same with the stop one. And then we're resizing those vectors that we're storing our state variables based on the joints that are passed in. So that's looking at these joints here and making sure that we allocate enough variables to store that information. All this section is doing now, you can see it's looping over all of the joints that were provided and checking it makes sense for a differential drive robot. So it's checking that there's only one command interface, and it's checking that it is a velocity interface, and then it's checking that there are two state interfaces. It's checking that the first one is position and that the second one is velocity. This is in a for loop, so it's going to be doing it for both joints. So it's checking for the first joint, do we have a velocity command interface, and then a position state interface, and then a velocity state interface, and then same for the other one. So it's very wordy, but all it's doing is just checking that the provided information is sensible for this hardware. If that's all good, we return successful. Great. Since this one's just the simulation, that's all the initialization that needs to happen, but we'll be putting some more things in there later. Next up, we've got these two functions. We've got export state interfaces and export command interfaces. As I said before, these functions are the way that we tell the rest of ROS2 control what our hardware interface has accessible. So what things can be commanded and what things we have state feedback on. And what it also does is it's going to link each of these interfaces with a variable inside the class. So for the state interfaces, if we update the local variable then that's linked to an interface, then when the rest of ROS2 control reads from that interface, it's going to get whatever value is in that variable. Likewise with the command interfaces, if the rest of ROS2 control writes into a command interface, then it's going to update the value of whatever variable is linked in it. So you might remember back in our header here, we had these three vectors. So a vector is like an array in C++. So the first one here is for our command velocities. The second one here is for our position feedback. and the third one is for our velocity feedback. So we're wanting to link the values of these variables in with the interfaces so that it links it to the outside world. So let's take a look at the export state interfaces. We've got a for loop here that's looping over all of our joints. So it's going to be 2, it'll be 0 and then 1. So it's going to loop over all our joints. Then for each joint, it's going to link the name of that joint. So it's getting the name. In this case, it'll be, left wheel joint. It's going to get the position interface for that joint, and it's going to link it to the corresponding value within that position feedback array. Likewise, we then want to add a velocity one. So for the joint with that name, we want to link a velocity interface to the corresponding value in the velocities array. Now you might be wondering where we got the joint names and stuff from. We're getting it from this variable info underscore. And back up here, we passed in the hardware info to the onInit command. And this base function call here, where we called onInit on the system interface, that secretly updates a hidden variable called info underscore to have the same as what was in the info that was passed in. So whatever we had accessible here in the onInit, we also still have accessible down here. So we can access that, we can get our joints, we can set up our state interfaces, and then we do the same thing for the command interfaces. So for each joint, we want to, for that joint, add a velocity command interface, and we want to tie it in with those command values. So now, whenever something updates this hardware component's command interfaces, that's going to update the values in these variables, and then whenever we put numbers into these values, it's going to update what the rest of ROS2 control sees. Then we move into onActivate. So you can see that this is just simulating, it's got a sleep here, it's just simulating some hardware that takes a long time to wake up, and it also initializes some values. So we're going to be getting rid of all of that soon and putting our own stuff in there. And then once it's finished activating, it prints out to the terminal and responds with success. Similar for deactivate. We've got some logging, we simulate a sleep to simulate something that's taking a long time to shut down, and we return success. Finally, we get to the read and the write, and to be honest, these are implemented a bit weirdly. Firstly, there's all this stuff here to do with differential drive kinematics. I don't know why that's there. All of that is also being handled in the differential drive controller. We could delete all of this and it wouldn't make a difference, so I'm not sure why that's in there. Secondly, the way they've implemented this demo is that the controls of the commands are fed straight into the feedback. And so they've implemented all of that in the read function. So it's handling the positions and the commands. And then the write function actually doesn't do anything. It just prints to the screen. So it's a little bit funny. It's a little bit confusing. I think we'll be getting rid of all of this when we do our own one. And hopefully it'll start to make a lot more sense then. Finally, there's this little line at the bottom that tells it how to export the plugin. So I know that was pretty rushed, but hopefully it's given you a bit of an idea of the structure of it and what's involved and that sort of thing. If you missed some bits, don't worry, because we're about to dive deeper as we rewrite everything to suit our own hardware, and I'm sure it'll all start to make a lot more sense then. Sometimes when you're trying to get all this to work, not only do you need custom software, you also need custom hardware. And that's where the sponsor of today's video comes in, PCBWay. You can send your PCB design off to PCBWay and they will custom manufacture it for you. You can get simple PCBs as well as more advanced ones like multi-layer or flexible. They can even assemble it for you, either using components from their suppliers or ones that you've provided. And if that's not enough, PCBWay also offers 3D printing, CNC and injection molding. So whatever your custom hardware design needs, check out PCBWay by following the link in the description. When it comes to developing with real hardware, there's a few different ways you can set up. One way might be to take the hardware out of your robot, plug it into your dev machine and develop on it that way. What I've chosen to do is leave all the hardware in the robot, and I've actually connected to the robot via SSH using VS Code's remote development tool. So this looks like I'm in VS Code on the dev machine, but it's actually connected remotely over SSH to the robot. So these files are files on the robot and this terminal is a terminal on the robot. And I've gone ahead and created a workspace and a source directory and cloned that same example2 directory that we saw just before. I've also got one that I prepared earlier. I'll be pulling some bits and pieces out of that so that we don't spend too long getting bogged down in code. When it comes to actually integrating the functionality for a particular piece of hardware, there's also a few different options we can take, and it'll depend a little bit on the particular hardware in question, the libraries that are available for it, and your personal preference. For example, a typical approach might be to include the library that's provided by the manufacturer of your hardware, and then you just call the functions of that library inside your hardware interface. In my case, I'm speaking raw serial to my hardware, so what I could do is put all of those individual serial calls into my hardware interface, but instead what I'm going to do is I'm going to abstract that away. I'm going to create a wrapper. So I'm going to have a different class, and it's going to handle all of my serial comms for me, and then I'm just going to call its functions in my hardware interface. This gives me more flexibility and modularity. So for example, if I want to ditch ROS2 control and make my own control system, I can do that more easily. Or if I want to change out for a different piece of hardware, I can also do that more easily. So I've put my whole abstraction into a header file. So we're going to go into our hardware directory, include before, here's where our other headers were. And I'm going to paste it in here. So it's called Arduino comms.hpp. Normally I would split this up into a header and a CPP file, but to make it easier for you to include if you want it, I've put it all in a header. And the details of this don't really matter too much. All we need to know is that we can include it and we can call these different functions like connect, disconnect, and read encoder values, that sort of thing. Also, if you're familiar with the previous version of my library, I've changed the dependency. It used to be based on a different serial package and now it uses libserial, but we'll deal with that later. So as I said, we don't really need to know too much about this file. We're going to include that in our hardware interface. So the first thing we're going to change here, where we've got all our includes, we're going to add a new include. We're going to go include ROS2 control demo. It's the same directory because this is where it's including the visibility control, but we're going to include Arduino comms.hpp. And we're going to also create an instance of that down here. So I'm going to actually get rid of all of these. We'll see later that we don't need any of them. And by deleting them, it'll make it easier to spot the things we need to change because they'll be broken with those missing. So we're going to create an instance of Arduino comms, and we're going to call it comms underscore. You can set this up so that you've got all the syntax highlighting and stuff. I haven't got that working at the moment, but that will make it easier. So we've created this comms object that's going to handle all of the comms to and from the Arduino, and now we need to call its functions inside these functions. So we're going to go into our Diffbot system implementation here, and the four things that we want to do are connect to the hardware, disconnect from the hardware, write from the hardware, so write the motor speeds, and read the encoder values. So I'm just going to kind of make some space for those things. So we're going to scroll down in this file. Here we've got on activate. So I'm going to get rid of all of this stuff in the middle. I'm going to leave the print statements because they're helpful for debugging. And I'm going to put this in a comment for now, but we're going to go comms.connect. So that's to remind us that's where we're going to do our comms connection. I'm just going to delete the other bits of this to make it neater. Then on deactivate, we're going to call comms.disconnect. So again, we'll put that there. In our read function, once again, we're going to get rid of all of this stuff. I'm going to get rid of the prints in here too. We don't really want too many prints in the read because it'll just keep spamming it out. So here we're going to have comms.read encoder values. And in our write, again, I'm going to delete everything in there and go comms.set motor values. So we've got these functions, we know we want to call them, but we're going to need a bunch of other parameters and information to set this stuff up properly. So we're going to head back up to the init function. And you might remember from before, here's where we read in from the hardware parameters. Now, because we've got so many parameters, I'm actually going to create my own structure for storing all the parameters in. You don't really need to do this, it just makes it a bit neater. So back in the header, we'll scroll up to here. I'm going to put it in here inside the class, so it's only accessible by this class. And I've just prepared this in advance. So it's a struct called config. we're going to store the left wheel name, the right wheel name, the loop rate, the serial device name, the baud rate, the serial timeout, and the number of encoder counts per revolution. Now that we've declared that struct, we also need to make an instance of it. So I'm going to go down here and go config cfg underscore. So now we've got an instance of our config. We need to populate this with all the parameters that came from our exacro file. So I'm going to head up and just copy this. So I'm going to swap back to the CPP file. We're in this onInit function. So remember, that's where our hardware info is getting passed in, where we're setting up all these parameters and that kind of thing. So I'm going to go ahead and paste those same list of variables there so that we know what the things that we're trying to read out are. I'm just going to clean this up a bit. So what we need to do, just like we saw here in the example, where it took the info hardware parameters and then the name of the thing, and then it converts it from a string into a double or an integer, whatever's appropriate, and saves it into those variables. So I'm going to go grab these. We only need one of them. And I'm going to put that at the end of each of these. And then what I'm also going to do is I'm going to take that variable name and put that as the thing that we're reading in, and we can get rid of all of this stuff because we don't need that anymore. So what it's going to do now is it's looking for parameters that have these names inside our ROS2 control exacro file. So up here in our description, so it's going to be looking for those parameters there. We'll put them in later, and then it will be converting them. Now we've got to check, at the moment I'm using S2D here, so that's string to double. But some of them are just strings, so the left wheel name, right wheel name, and device are just strings, so we don't need to convert them at all. And baud rate, timeout, and encoder counts per revolution are integers. And finally, loop rate is a float, not a double, so we should change that to... Oh, and I forgot, all of these are inside our config struct. So I'm just going to go cfg underscore dot. Okay, so what our onInit function is doing now, it's going to be reading our hardware info parameters, getting the parameters with each name and assigning them to their appropriate members of our config struct, and then we'll be able to access them from anywhere else in the system that we need to. So we can now go ahead and populate that connect call. So that was down here in onActivate. So if we take a look at our Arduino comms and find the connect call, it takes in the serial device as a string, the baud rate, and the timeout in milliseconds. So we're going to uncomment this, and we go cfg dot device, cfg dot baud rate, cfg dot timeout ms. Also, while we're here, the disconnect function actually doesn't have any arguments, so we can uncomment that one. So that's the connection and the disconnection. All of the other parameters we've got are to do with our wheels, and they're actually going to handle them a bit differently. So I've got another header file that I'm going to just paste in here from somewhere else. It's called wheel.hpp, and you can see it's pretty simple. It's pretty much just a struct with a couple of other functions on it, and it stores all of the information that we might want to associate with a particular wheel. So we've got the wheel name, the current encoder counts, the command velocity, the feedback position, the feedback velocity, and also the number of radians per encoder count for this wheel. So we can use these to kind of clean up our code a little bit. So in our header, we've got to make sure we include that. So I'll copy and paste that other one, and we'll place that with wheel.hpp. And then I'm going to create an instance of our wheel, wheel L, and wheel R. So if we go back into our initialization routine, we want to set up our wheels. So I'm going to go wheel L. If we go to our wheel.hpp, it's got a setup function that takes in the wheel name and the number of counts per revolution. So wheel L.setup, so that'll be cfg.left wheel name, cfg.encoder counts per revolution. If you want to modify yours so that you had a different number of counts per revolution for the left wheel and the right wheel, you could easily make that happen here. So I'm going to paste that, and we're going to do the same for the right wheel name. Now that we've set up our wheel objects, what I want to do is I want to tie these variables that are part of the wheel object, I want to tie them into our exposed interfaces. So you might remember before in our export state interfaces and export command interfaces, there were these arrays, and it kind of iterated over the vector and linked each of the elements of this vector with a state. Instead, what I'm going to do, I'm going to get rid of the loop. And what I'm going to do is I'm just going to hard code these to have two different joints, one for the left wheel and one for the right wheel. So we'll work on the left wheel first. So the name of that joint is going to be in that wheel L.name. We've got the position interface. Now, instead of that being that value there, I want to link this up to wheel L.pos. Then same name for the velocity interface, and I want to link that one up to wheel L velocity. Then I'm going to take this whole block and copy and paste it. And modify it for wheel R. So what this function is doing, declaring a vector of the state interfaces. This is all the state interfaces that we're going to export to kind of the world. We're going to add one that is a position for the left wheel tied in with the left wheel position variable. One that's the velocity of the left wheel tied in with the velocity of the left wheel variable. We've got an interface for the position of the right wheel with the right wheel's position variable, and a velocity interface for the right wheel tied in with its variable. So I hope that makes sense. And pretty much exactly the same thing for the command interfaces. So we're going to delete these. I'm going to copy that wheel L name there, and this time it's going to be wheel L CMD, and we're going to make that wheel R. So we've got a command interface for the velocity of the left wheel and the right wheel, again, tied in with those variables of the wheels. So with that done, any time that we update these position and velocity members of our wheels, then that's going to tell the rest of the ROS2 control system that those wheels' position velocity has moved. And any time that the rest of ROS2 control sets the velocity of these wheels, then it's going to change the value of this command member. So we can make use of that down in our read and write functions. So let's do that now. We'll start with the write because it's easier. So you might remember that this hardware actually takes the motor values in encoder counts per Arduino loop. So we're actually going to convert that number. So we'll go motor L counts per loop, and that's going to be equal to our wheel L dot command. So the command is going to be in radians per second. Then we want to divide that by wheel L dot radians per count. And we want to divide that by the general loop rate. And we'll do the same thing for motor R. Oop, I better fix these up. So this should give us the number of counts per loop for each of the two motors, and then I can just simply pass those into my function. Again, make sure I change this to motor R. So this will tell the Arduino to set those values. Just remember that this variable is actually called rads per count, not radians per count. Now read is a little bit trickier. So we'll start with this read encoder values function. If we go back to our comms, you'll see that this function takes in the two values by reference. So it's going to save the encoder values into whatever variables we pass in. So I'm going to pass in wheel L.enc and wheel R.enc. So that'll read the encoder values into those variables. Now what we need to do is we need to turn those encoder values into a wheel position, so that's in radians, around, and velocity, which is going to be in radians per second. Calculating the position is not too bad. There's a function to help us for that. So if we look at our wheel.hpp, it's got calc_enc_angle, and so this function converts the encoder value, multiplies it by the radians per count to give us a value in radians. So we can go wheel L dot pos equals wheel L dot calc enc angle, and of course same for the right wheel. What about the velocity? So to do the velocity, what we want to do is we want to look at the previous position value and the current position value, see how much time has passed between them, and divide the difference by the difference in time to give us a velocity value. So to do that, what we need to do is we need to store the previous value. So we'll go float pos prev equals that. So we'll store the previous position. Oop, I've just realized I missed another R there. So we'll store the previous position into a variable. And then what we want to do is we'll say wheel L dot velocity equals the new pos, so wheel L dot pos minus pos prev divided by, and I'm going to go delta seconds. Now, this delta seconds needs to be the amount of time that has passed since the last time we ran this. You might think, where are we going to get that from? We could start a timer each time and check it, but we actually get this given to us. So we see this function comes with an RCL CPP duration period. So I can go double delta seconds equals period dot seconds. And while I'm at it, I just realized this should probably have been a double as well. So there we go. We've got the position and the velocity for the left wheel. I'm going to copy that pretty much the same behavior for the right wheel. So let's just check over what this function's doing. We read the encoder values. We calculate the number of seconds since the last time we did this. We store the previous position for the left wheel, we calculate the new position, and then we set the velocity to being the difference between the new position and the old position divided by time, and then we do the same thing for the right wheel. Now there's plenty more we could be doing here in terms of error handling and that sort of thing. For example, every time we're reading or writing from the comms, we should probably actually check that it's connected before we try and do that. With the position calculation, there's probably going to be an issue of overflow where the encoder counts wrap around. So you can go through, you can deal with that. You could change your velocity calculation to be more smooth, all sorts of stuff you can do, but this should do us for now. We're just about ready to build. However, we do need to add the dependency on the new serial library. Now, because it's not a proper ROS package, we kind of do this in a bit of a funny way here. I'm just going to add an extra line here that says target link libraries. Now the name of the target here is ROS2 control demo example 2, and we'll make this public, and dependency on the serial library. So this will link it to a library called serial. Confusingly, the old library was also called serial. We also want to make sure it's in our package XML. It's just a good thing to do. So it's a system dependency on libserial-dev. And if you haven't already got it installed, you want to install it with sudo apt install libserial-dev. In my case, I've already got it installed. So we should be able to now build with Colcon. Hopefully I haven't made any mistakes. So we'll go Colcon build symlink install. Can't spell build. While it's doing that, I'm going to go ahead and install this extension. Okay, so that finished building. Now, something I just realized, I'm going to go back into here, we did not update our parameters here. So again, I'm just going to magically pull them from somewhere else. So we've got left wheel name, right wheel name, loop rate, serial device, baud rate, timeout, and encoder counts per revolution. We built with symlink install, so that should be fine. I'm going to open up a new tab. I'm going to source our workspace. And let's try and launch it. So ROS2 launch, ROS2 control, demo example 2, diffbot.launch.py. We'll find out what mistakes I've made. I did remember this was a thing. The one I copied, I changed the name from timeout to timeout ms. So let's just try running that again. All right, that's looking good. Now the RViz isn't working properly, but that's fine. So now I'm going to try and run teleop. So ROS2. Hopefully I got that right. And now I should be able to drive the robot. So look at that. Our hardware interface is working. It's talking to the rest of ROS2 control with the diff drive controller, and I can control the wheels with my keyboard. If you're having any troubles with it, you should be able to put in print statements. So we can see if we look at this, it should have printed out when it, look at this, we've got loading hardware, initialize hardware, configure hardware, successful configure of hardware, activate, blah, blah, blah. So all of these things get printed in there. Now that we've implemented our functionality, let's rename the project so we can call it whatever we want. So let's go back to one of our files and we'll start stepping through this. So we'll start with these macros. We've got all of these big capital letters, ROS2 control demo example 2. So I'm going to highlight that and go Control Shift F. I'm going to make it case sensitive, and I'm going to restrict it to files in our source directory so it doesn't get all the build files. So we can see we've got it in 3 different files there, and we're happy to replace all of them. So I'm going to replace all of them with diff drive Arduino. That's the name of my one. You want to replace it with whatever you're calling yours. So replace 33 occurrences across 3 files. Yep. All right. So look at that. So many of them. Now we can go ahead into diffbot system. What else do we have here? We're going to have the lowercase one. So the same thing, but all the times that it's lowercase. So again, in a whole bunch of places, it's actually in quite a few more places this time. So we'll go ahead and replace all of those with diff drive Arduino. Gotta spell it right. Arduino lowercase. Finally, we've got our system hardware. So diffbot system hardware. So let's call that diff drive Arduino hardware. Then the other thing we want to do is rename this directory. So I'm going to right click that, go rename, so diff drive Arduino, and same with the actual root directory. None of this example 2 nonsense. We'll go diff drive Arduino. So what I'm going to do here, I'm going to delete our build and install directories. Just helps to kind of clear the air a bit and build it again. And if we've replaced everything correctly, it should still build, but have the new name. Oh, forgot to rename this file. While that's building, we'll actually take a look at that file. So this tells ROS2 control kind of how to load the plugin. So it says, here's the library path. It tells you the name of the plugin, the base class, and then it's got a bit of a description. So you want to update that to suit your hardware. All right, that's successfully built. So we should be able to source our workspace again and run that same thing, except this time, instead, we're going to launch it as diff drive Arduino. And I think that should all be the same. So it still works exactly the same, but now it's got our own name. Yeah. Now I'm sure there are many changes and improvements that we could make, but there are just a couple I want to do to start with. So you might remember earlier in the video, I said that with all of these different functions that we can override, the connection and disconnection from the comms should actually happen in onConfigure and onCleanup rather than in onActivate and onDeactivate. So I'm going to copy and paste these on activate and on deactivate functions. And I'm going to rename this one on configure and this one on cleanup. So then in our CPP file, we're going to do the same thing. So here's our on activate and on deactivate. So I'm going to copy and paste them. So these ones I'll rename just like the header. And I better rename this. So now we've got the comms connection, disconnection in the configure and cleanup. We can get rid of them from the activate and deactivate functions. So at this point, these functions aren't doing anything anymore. So we could get rid of them if we wanted to, but I'm going to leave them there in case you've got something you might want to do with them. Remember, these are for anything that you want to happen when you're about to start or stop using the motors, the actuators. So in my case, I haven't got anything for the deactivate, but for the activate, I'm going to set the PID values for the motor control. So that's comms.set PID values. And I know the numbers that'll work for me are 30, 20, 0, 100. I've just hard coded those numbers there, but for the final version that I'll put up on GitHub, I'll make these numbers configurable. I'll also go through and clean up and change a whole bunch of other things. But for now, this should be working. So we should be able to go ahead, rebuild and rerun to check that moving these stuff into those other functions works all right. So we're now seeing here we have configuring, please wait, successfully configured, configure hardware, activate, activating. So it's all happening in the configure now, and again, still works same as it did before. ROS2 Control is a powerful tool, but writing your own hardware interface can be pretty daunting for a beginner. So I hope you found this video helpful and useful, and that you've been able to go ahead and implement something custom for your own project. The finished code, possibly with some further tweaks, will be available on GitHub. You can find a link to that in the description. If you've got any questions or comments, there'll also be a link to the corresponding discussion thread over at the Articulated Robotics forums. Thanks again to PCBWay for sponsoring this video, and thanks especially to the patrons over at Patreon for supporting me to not only write and share code like this, but also to spend time sitting down and explaining it to you. If you found this video helpful or useful, please consider joining. This is also going to be my last video filmed in this location. We're moving house next week, so you can look forward to a new set, and there'll be a Patreon exclusive video exploring the new space and what it's like. So I'll see you there.